Hello, everyone. Welcome to EE406. So, we will start with our lectures today. And the first topic that I will try to cover is essentially nonlinear systems and linearization. Um, so, you will see that in 406, almost or many of the systems that we will take a look, including pendulum, inverted pendulum, and so on, will actually be nonlinear systems. So it will be very useful to cover how we will deal with such systems. In fact, if you remember from 407, we started talking about nonlinear systems because we also had nonlinear systems in 407, and we briefly touched upon linearization, linear approximations, and deviation variables. So essentially in 406, I will try to cover that from a state space perspective in a slightly more formal way. Okay, so let's basically put our title here. We are at week one. Okay, and let's say linear uh, approximations and linearization. Okay. So, why are we interested in finding linear approximations to nonlinear systems? Well, the reason is that we have very limited tools in trying to deal with nonlinear systems. Okay, when we face a nonlinear system, one of the things that we will attempt is try to find whether there will be an operating point. In fact, we will see that we will define something called an equilibrium point again. And around these equilibrium points, we will have very useful properties and we will be able to find linear approximations. And those linear approximations will be valid only around that equilibrium point, but will give us the ability to design controllers by using all the tools that we have learned previously, like in 302 and so on. Okay, 302, 407, and so forth. Okay, so why linearize is that is the difficulty of general tools for nonlinear systems for analysis and design. Okay. And conversely, the abundance of such tools, conversely, for linear systems. Okay, so I will first start with defining linearity. Okay, so what is linearity? Let's remember that. And this concept is very important and actually is always asked over and over again, okay, in exams, in juries, and stuff like that. So it's really useful to remember that, okay? So let's say that we have a system for this purpose, a single input, single output system, okay? But it's an nth order linear system. And let's also suppose that it has also an output y, and this basically is a single input, single output linear system. That means we have u being an element of r and also y being an element of r as well. Okay. So we define linearity not only with respect to the system input, okay, but in terms of system input, output, but also the initial conditions. Conditions. Okay, so let's say that in general, okay, y basically is a function of time. So it's a function of time. It's a function of initial conditions. Remember, this is an nth order linear system. So we have x0, the initial condition, as a vector, and also the input u. Okay. Now let's try to make a definition for linearity. Let me choose a slightly different color. Not a slightly different color, but the definition is definition of linearity. So the system given above, the system is linear if and only if, this is usually abbreviated as IFF, a number of properties hold for the input, the initial conditions, and the output. Okay, so here are the properties. Okay, so first of all, if we want to write the output, okay, which I defined above, it has to be the additive combination of two components. One in which the input is 0, but there is an initial condition, and another one where the initial condition is 0, but you have an input. Okay, so basically you have y t x0 non-zero, 0 of t. This is a 0 function, plus another component where you have 0 as the initial condition. Remember, this is again a vector, but you have a non-zero input. Okay. Now here you have different names for that. This one is called the zero input response. And the second component is called the zero state response. Okay. Now let's also consider a second property. That's not a nice color. Let me change that. Let's continue with our color here. Second property. Again, if you have, now if the input is a combination of a number of different signals, so that means if you are trying to find for a zero state response for a combination of different signals at the input, a linear combination, that means alpha times u1 of t plus beta times u2 of t at the input, the response to that should be a combination of two responses specifically for each one of those signals. So let me write that. Okay, so that output for a combined input should be equal to the combination of the outputs. That means alpha times y for t 0 u1 of t plus beta y t 0 u2 of t. Okay, so you see that if the input is a combination of two signals u1 and u2, a linear combination where it's a weighted combination, weighted by alpha and beta, the output is the individual responses for these two signals combined with the same weighting coefficients. Okay, so that's a property that needs to hold. Furthermore, this property should not only hold for the input, but it should also hold for the state, the initial state. Okay, so if you have a zero input, but you have a combined initial state, alpha x01 plus beta x02, these are two initial states, but you have 0 of t at the input, you should have the same property holding. That means you should have alpha times y t x01 at the initial condition, 0 of t, plus beta times y t x02, 0 of t. Okay, now you see the last two actually have a special name. Okay, and this is known as the superposition principle. Okay, the superposition property that really comes over and over again. So it's really beneficial to uh, have a good grasp of the definition of linearity in terms of these three properties. Okay, and this is for a system which can have an input and which can also have an initial state. So linearity is not defined in terms of only the input-output relationship, but it's defined also in terms of the initial state and the output relationship as well. Okay. Now let's, after defining this, let's move on to our system representation. Okay. So nth order linear system. Okay. In state space form. Still, we are considering a single input, single output. You would remember from 302 that this is not necessary. We can in fact define an nth order linear system in state space having m inputs and r outputs as well. So state space representation allows multiple input and multiple output systems as well. Okay, so remember the definition. We have the derivative of the state defined as a linear function where the derivative of the state is equal to a matrix A times the state vector plus B times U. Here we have the A matrix, essentially an element of R to the power n by n. So it's a square matrix. Okay, because we have a single input, B is essentially a column matrix, which is n by 1. If you have multiple inputs, B also becomes a rectangular matrix, depending on how many inputs you have. Okay. Similarly, the output equation is also a linear equation and is given by y is equal to cx plus du. Again, here we have, by the way, here y, u are scalars, and we know that x is obviously an n vector. Okay, and therefore the other matrices, C and D matrices, are given by essentially are elements of 1 by n for the C, because you have a scalar output but an n vector state, and also D in this case is simply an element of R. Also remember, again from 302, is that the transfer function for the single input, single output system is given by simply C times Si, I being the identity matrix, Si minus A inverse B plus D. Okay, so that's the transfer function. And only for a single input, single output system, we have a single transfer function. If you have multiple inputs and multiple outputs, in fact, you will end up having a transfer function between each input and each output separately. So you will have a transfer function matrix in a sense. Okay. Also remember, for nonlinear systems, okay, the transfer function representation, remember, this is nothing but a form of a mathematical model, right? Mathematical model does not exist. That's a drawback of a transfer function representation. It's only defined for essentially for linear systems with zero initial conditions. Okay, and but we will use, for such systems, for nonlinear systems, either the state space representation, and or the differential equation representation. Okay, so state space, in fact, state space representation is, remember, a set of first order differential equations. So it's a coupled set of first order differential equations, n of them, but you can combine them into an nth order differential equation representation as well. So both of these are both are time domain representations. Okay, versus the transfer function, which is a frequency domain representation. Right? Okay, so how do we represent a nonlinear system in state space? Okay, so an nth order nonlinear system in state space representation basically is given by the derivative of the state being a nonlinear function of both the state itself as well as the input. Now, f is a vector valued nonlinear function, okay? And also the output being another function. In fact, in this case, it's not a vector valued function because we defined y as essentially a scalar, okay? But okay, let's define it in general. So u also can be a vector. Therefore, a y can be a vector, so a multi-input, multi-output system. In this case, both f and g are multi-valued functions of both the state and the input variables. Okay, so f and g functions, this sub-bar indicates a vector valued function, are in general vector valued nonlinear functions. Nonlinear functions of multiple variables. Okay, let me give you an example. By the way, in this case, obviously x is Rn. In this case, u is R, let's say Rm, and y is an element of R L. Whatever. M is the number of inputs and L is the number of outputs. Okay. Let me give you an example of a multi vector valued nonlinear function. Okay. So that means f bar is actually equal to a vector of, let's say, f1 of multiple variables and fn of multiple variables. Okay, so f bar means it's actually a function of a vector of functions. Okay, so let me break the file here, and then I will come back with an example, a simple example that will be actually, let's say, the most common example, or the example that you will encounter as part of the laboratory work as well.